Hello students, I have brought another video which contains more reasoning questions from the chapter Haloalkanes and Haloarenes. Part 1 has already been shared with you. So here are the remaining questions, the most important questions. So these two videos will cover almost everything which is related to the reasoning of this chapter. So the first question in this video is alkyl chlorides on treatment with aqueous KOH leads to the formation of alcohols, that means alkyl chloride or halide in general, on reaction with aqueous KOH, that is a strong base potassium hydroxide is taken in aqueous medium, so it leads to the formation of alcohol. But if you carry out the same reaction in the presence of alcoholic KOH, that is the reaction between alkyl halide, alkyl chloride here in this particular question specifically, generally alkyl halide, in the presence of alcoholic KOH, then you get alkene as the major product. So the reason for this question is that in an aqueous solution, KOH almost completely dissociates to give you OH ions, which are strong electrophile, as you can see here. I have highlighted the keywords, the most important words which must be in your answer. So OH ions, they are very strong nucleophile, so it undergoes nucleophilic substitution reaction, that is in place of Cl, OH comes, nucleophilic substitution, and you get the alcohol as a product. On the other hand, when you are taking alcoholic solution of KOH, then it is going to produce alkoxide ion. Now alkoxide ion is a very strong base. RO minus can abstract H plus easily. So that's why it starts elimination reaction, and in place of alcohol you get the corresponding alkene. That's the answer. Next question is, the boiling points of chlorides, bromides and iodides are considerably higher than that of the hydrocarbons of comparable molar mass. So they are talking about the alkyl halide, and the comparison of alkyl chloride, bromide and iodide is with hydrocarbon of comparable molar mass. So reason is obvious that there is polarity. There is polarity in alkyl halide. The CX bond in alkyl halide has polarity in it. Because of that, a dipole develops here, that we can show as delta positive and delta negative. A dipole develops here because of this dipole-dipole interaction as intermolecular force of attraction between alkyl halides and their higher molar mass as compared to hydrocarbons. We generally take hydrocarbons with the other compounds, they should be of comparable molar mass, but still if you compare hydrocarbon with the alkyl halide, the halogens have more mass than hydrogen, so there will be increase in mass. The most important reason, the first reason, the prominent reason for this particular question is polarity. Along with that, you can mention higher molar mass of halides also. Next question is, explain the following pattern of variation of boiling points of different halides with the same alkyl group. If I take methyl group here, in all the four it will be methyl group. If I take isobutyl, in all the four it has to be the same alkyl group. Only then I can compare that why the trend is like that. Only then I can justify this, that I am changing the halide but I am keeping the R group same. So whatever variation is coming, that is coming because of the halide. Now this is very clear here. The iodide is having the highest boiling point and fluoride is having the lowest. When you talk about halogens, fluoro, chloro, bromo, iodo in the periodic table, when we move down this group, the size and molar mass of the halogen is increasing. Because of that, there is increase in van der Waals force of attraction. Increase in size means increase in surface area. And if that is increasing and mass of halogen atom is increasing, the magnitude of van der Waals force of attraction increases. That's why the trend is like that. Generally, the reasoning questions are asked for 1 mark. It may be a 3-mark question with 3 parts. So, 1 mark for each part. So, you should know how to answer a particular question to the point. So, these keywords must be there. And if they are asking you a particular question, reasoning question only, but that has 2 or 3 marks, then you have to explain it accordingly. You can't just finish it in 1 line. So if you use this presentation along with NCRT and you understand everything and then practice by writing, then you know how to express your answer, and believe me, you will get full marks. In chemistry, it is very easy to score 100. The only thing is written practice, regular practice is required. Okay, the next question is the boiling point of isomeric haloalkanes decreases with branching. Explain. Again the same thing. When branching is taking place, the surface area of the molecule decreases. For example, if I take a straight chain, 5 carbons, I'm talking about pentane, N-pentane. You can complete the hydrogens, the structure by putting hydrogens here. And if you draw its isomer, so I will start with branching. I put 1 branch. In the next one, I am putting 2 branches. So these are the isomers of pentane. Now you will see that when you are moving from here to here, when the branching is increasing, then the surface area is decreasing. And if the surface area is decreasing, the intermolecular forces of attraction, van der Waals force of attraction, is also going to decrease. That's why the boiling point of isomeric alkanes, haloalkanes, decreases with branching. Next question. The para-isomer of dihalobenzene has high melting point and lesser solubility. See, the trend is opposite. High, and here it is less soluble as compared to ortho and meta isomers. They are talking about dihalobenzene. So you have benzene. If there is 1 chloro here or any halogen, in general you can write X. This will be the ortho isomer. The next is meta isomer, and this one is para isomer. Now the question is saying that the para isomer, that is this one, is having high melting point. As you can see, it is symmetrical. There is symmetry, and anything which is symmetrical fits into the crystal lattice very well. And to disturb that crystal lattice, to break the bonds, we have to supply more energy. So melting point increases. But why the solubility is less? Again the same reason. If it has to dissolve in a particular solvent, it has to make bond with the particular solvent in the process, then the earlier bonds have to break. So again, if the bonding is strong, because the symmetry is there and it is fitting in the crystal lattice, the solubility will decrease. So para isomer is more symmetrical, first thing, very important. And then this means that in the crystal lattice, the molecules of the para isomer are more closely packed. It fits very well. You get a perfect structure, almost perfect. As a result, the melting point is higher and the solubility is lower. Next question is, haloalkanes are polar in nature, but they are very slightly soluble in water. Now we know that like dissolves like. We always say that there has to be a particular solvent, like a polar solvent, in that the solute with polarity will dissolve. Right, and if there is a non-polar solvent, then the solute should also be non-polar. So their nature has to be same, solute and solvent's nature. That we call like dissolves like. This phrase is used to explain that. Now haloalkanes, they have polarity in them. Water is polar in nature. Then why they are very less soluble? The reason is, in water, one water molecule is having H bonding with the other water molecule, quite strong bonding, and one alkyl halide CX bond is there is polarity. So this dipole will be having dipole-dipole interaction with its own kind. Now this H bonding is very strong. When you try to dissolve haloalkane in water, then the already existing strong bonds have to break completely. Only then it is something going to be completely soluble. But here, the intermolecular attraction between halogen and water molecule is going to be weak, less than the original water molecules, because in the water molecule, water is a pure solvent, it was having hydrogen bonds between the molecules. That's why the new bonds were not that strong. So it is only slightly soluble. A very commonly asked question, this one, why Grignard reagent, that is RMgX, must be prepared under anhydrous condition. There should not be moisture, there should not be water in the container. What is the reason for that? So the reason here is very simple, that Grignard reagent is very reactive, highly reactive reagent, and it reacts with any source of proton to give hydrocarbons. Grignard reagent is RMgX, right? So if I have this RMgX, see the nature of this R group. Generally we write Rx, and it is fixed in our minds that R is positive, X is negative. But here R is making a bond with magnesium. Magnesium is a metal, so R will be having the negative charge here, and magnesium being a metal is always electropositive in nature. So if R is getting proton, that is H plus, from any source, it is going to give you RH, that is alkane. That's the reason that if there is water, in the question only water is asked, but I would like to tell you here that it may be alcohol, it may be amine, which are sufficiently acidic to convert them to corresponding hydrocarbon. Now amines are not acidic in nature, but when you put amines in water, when you are taking the aqueous solution, then amine will be converting to RNH3 plus, and that way in water it can also provide H plus. So it will be in a way speeding up the process, you can say, right? So that's why Grignard reagents are very reactive, and they should not be prepared in the presence of any source of proton. Generally they ask you about water, because this question is from NCERT as it is from the exercise portion. So the answer is because it reacts with water by you can see the reaction here, and produces alkane, RH, along with magnesium hydroxyhalide. Next, although chlorine is an electron withdrawing group, yet it is ortho-para-directing in the electrophilic aromatic substitution reaction. A very important question. It's a solved example from NCERT, and it is generally asked for 2-3 marks, because reasoning involves your resonating structures along with the explanation. Now the question is, this chlorine on benzene is electron withdrawing group. Why should it be electron withdrawing? Because chlorine is electronegative in nature. So this is bonded to carbon, so this should act as electron withdrawing group. But when you see the reaction, electrophilic aromatic substitution, then you will get the products ortho and para products. The reaction gives you ortho and para, it does not give you meta. So we have to give explanation for that. Now see carefully what is happening when an electrophile is coming in contact with chlorobenzene. Then if I am getting the ortho product, suppose I explain it using just one product, ortho. So the electrophile is attacking at ortho. At this carbon there is already hydrogen there. On each carbon you have one hydrogen, these 5 carbons, and on this one you have chlorine. So this double bond has broken. These 2 electrons are used in making the bond with electrophile here, right? And the positive charge is coming at the carbon which is attached to Cl. Now this is the intermediate, and it will go further only if it is stable. If this is not stable, the reaction will go back here. It will not go further. But it has been found that the reaction provides us ortho and para products. So we are trying to explain how that happens, right? This happens because here this carbon which is developing a positive charge is in the need of electron. If chlorine shows its electronegative nature, if it shows the inductive effect and takes away electron density from carbon, this intermediate, the whole intermediate will destabilize. But it must be stabilizing. That's why the reaction is going further. नहीं तो reaction रुक जाएगा ही नहीं आगे. It will go backwards. So how is that happening? That is happening because here chlorine, instead of showing the inductive effect, it is showing the plus R effect, resonance effect. It has 3 lone pairs. So it is offering the lone pair here and the reaction proceeds. So you are getting, I'll just show you the answer. The inductive effect, chlorine, if inductive effect is dominating, then through that chlorine is going to destabilize the intermediate. But if resonance is taking place, then halogen tends to stabilize the carbocation because it will provide its lone pairs. And the effect is more pronounced at ortho and para if Cl is giving the electrons towards benzene. Inductive effect is stronger than resonance, still the reaction is proceeding, right? And if inductive effect is there, then there will be deactivation of benzene. Deactivation means it will give you meta product. Ortho para will not be formed. But whenever you carry out this reaction, it is always ortho and para, meta nahi banta. That means the reactivity is controlled by the inductive effect, but the orientation means that where will the electrophile attack, ortho para pe ya meta pe, that is called orientation. Orientation is controlled by resonance effect. So resonance effect is taking the reaction further. Chlorine offers its lone pair to show plus R effect, positive resonance effect. It stabilizes this carbocation and the reaction moves further to give you the product. Next question is, aryl halides are extremely less reactive towards nucleophilic substitution reactions. And here the question can be extended to, aryl halides are extremely less reactive towards nucleophilic substitution reaction as compared to alkyl halide. Aryl halide, alkyl halide. So we are comparing that why is this less reactive. So whenever you look at this and this, one thing that should come to your mind instantly is that there is a resonance possible. And because of resonance, it will be having a double bond character. And it is difficult to break the CX bond, which is not a problem here. Here the CX bond breaks quickly and the nucleophile can come and attack here. So there are 4 reasons actually to this. First reason is resonance, as I just told you, that the CCl bond acquires a partial double bond character due to resonance. As a result, breaking of the bond, CX bond, is difficult, right? Second reason is difference in the hybridization of carbon atom in CX bond. If you have haloarene or aryl halide and you compare it with say CH3X, then you will see that here this carbon of CX bond is sp2 hybridized, involved in a double bond. This is sp3 hybridized. So here you have more S character. More S character means the carbon becomes more electronegative and it can hold the electron pair of CX bond tightly. So if it is holding the electrons of CX bond tightly, X cannot go out as X minus easily. So if X minus is not going out, how will the nucleophile come and show the substitution reaction? So this is the second reason. Third reason is that instability of phenyl cation. When the reaction is proceeding, suppose we say that this will break from here and it will give you X minus along with this. This is phenyl cation, this one. Now this is formed as a result, but this is unstable because same carbon is involved in a double bond and same carbon is having the positive charge. So resonance is not possible. That's why the SN1 mechanism, which proceeds via formation of carbocation, is ruled out. And the last reason is benzene is called electron rich because it has 3 pi bonds. Nucleophile is also called electron rich species. Now, if two electron rich species are coming in contact with each other, they will definitely repel each other. So, these are the 4 reasons that why aryl halides are extremely less reactive towards nucleophilic substitution reaction. If this question comes for just 1 mark, then very smartly you can sum up it in 2 lines. You must mention resonance, and along with that maybe just one more reason. All 4 are not possible for 1 marker. In 2 marker question, you can give all 4 to the point, smaller answer than this, so that you can get half a mark for all 4 and the total is 2. So this is how you have to strategize and make your answer very good answer. You have that concept in mind, but unless you do written practice, you don't know how to express your answer. So these presentations I am making for that purpose only, so that you know how to answer a particular question. Next is why chloroform. Chloroform is CHCl3. Must be stored in closed dark colored bottles. The bottle should be tightly closed. It should be a dark colored bottle, and it should be completely filled up to the brim. If that is not done while storing it, then what may happen that it will slowly oxidize in the presence of air and light. To avoid its contact with the air, we are keeping it filled up to the brim so that we don't leave any space for air on top of the liquid. And we are keeping it in dark colored bottle so that it's not coming in contact with light also. Because if chloroform is coming in contact with oxygen from the air and light, then what is going to happen? It will produce a very poisonous gas, that is phosgene. Carbonyl chloride, phosgene, quite poisonous. So to avoid this, we keep it in a closed dark bottle filled up to the brim. So that is the end of the second presentation also. I have tried to incorporate all the questions, most of the questions, reasoning based questions from the chapter Haloalkanes and Haloarenes. Now next presentation would be based on alcohols, phenols and ethers, IUPAC nomenclature from NCERT. I'll take the salt examples, the other in-text examples, as well as some exercise questions to explain the IUPAC nomenclature. I hope the presentations will help you. Thank you.